what I'm going to share with all of you today is a space shuttle tether mission that's going up in the year 2000. Actually, I've got two shuttle tether missions going up, one in 2000, one in 2003. Today I'm going to focus on the one that's happening in the year 2000, and that's actually late 2000 what we're looking at going on. And it's a combination of missions. It's going to be a mission to test out several engineering systems that we're going to fly on the 2003 mission. And also we're going to be conducting some science experiments with the University of Texas at Dallas, which I'll briefly cover. And then actually we're looking at this being a chance for kids in K through 12 to participate in this flight. Now a little background of space tethers. Right now to date here, NASA, the various commercial enterprises, and certainly Meyer Corporation have expressed an interest in exploring and utilizing space tethers in a wide range of applications. And the first mission that got that going was the TSS mission, which I'm not going to go on and on about. I've been doing that all weekend. But essentially from that point on, NASA has looked at further applications of space tethers and where they can be applied. A good example that they're looking at using space tethers, for example, is in microgravity research, because we can actually take a payload and take it a distance, some distance from, let's say, the shuttle at International Space Station, and you can create a variable microgravity environment where instead of being, 10 to the minus 6 Gs, we can maybe make a little more gravity there, okay? Where we can vary that environment and see the effects on various manufacturing processes. Another thing that they're interested in is a payload return to Earth. One idea that's being thought of is with the space station, instead of waiting for the shuttle to show up to take waste back to Earth, maybe just have a giant garbage container and tether that down, kind of like an elevator, and when it gets down far enough, you cut the tether from the station and the whole thing falls back to Earth. And as a variance of that idea, as maybe they have a science experiment on the shuttle that they need to return to Earth, and they would then return that payload down and it would return look like an Apollo capsule so it can survive re-entry, and then parachute and land, and actually think of some sort of helicopter capture scheme. One idea that really is becoming of concern lately, and something that we're looking at utilizing our technologies for, is orbital debris mitigation. A lot of the problems that happens on a shuttle flight is, or not shuttle flight, like a Delta or a Titan or an Ariane, is a lot of times you have these spent second or third stages left in orbit, which basically become very large debris in points of collision in space. And as a matter of fact, I believe last year, wasn't there a second stage Delta II came very close to hitting a German science experiment that was deployed from the space shuttle. So that's something that's becoming a big concern, and in the near term they're going to require that launch vendors and satellite manufacturers provide a mechanism to bring their dead vehicles back to Earth and not orbit as debris or points as collision. One thing we can use a space tether for, and what we're looking for, is if we take a dummy mass so big, weighing 20, 30 pounds, ejecting that from a spent stage and tethering it to let's say the spent stage of a Delta, there's enough atmospheric drag that tether will encounter. So instead of that stage being in orbit for 5-6 years, it may be in orbit for only a month or a week or a day. So it turns out there's enough with the solar wind in the upper atmosphere, enough to slowly quickly I should say, bring that back to Earth. The air up there is very rarefied, but the satellites or the spent stages are moving so fast that it feels enough of a breeze that it brings it right back down. Another use that we're looking for our deployer system, which we're going to talk a little bit about today, is momentum transfer. Have you ever, as a kid, or as a grown-up, I should say, the man. Okay. Matter of fact, since we're talking about some of this, I can now show you a pretty picture. I think a little backwards here. This, by the way, is this payload recovery waste management I was just talking about, where it return and parachute down. And this is the variable micrograv laboratory. And one idea is that this section here would crawl along the tether, creating that adjustable gravity in the laboratory here. Again, going back to this momentum transfer, it turns out what I was saying is, a kid, you take a bucket on a rope and you swing it around really fast and then you let go. Well, you can do the same thing with space tethers, where if you have that satellite, let's say this is something they want to do with SEDSAT last year, is take a small payload tether to the shuttle, and once they got far enough out, or once they hit apogee, they cut that tether and it flings that payload to a higher orbit. And I believe for the SEDSAT mission, if they did not use a tether, it would have been in orbit for, I believe it was like 90 days, and then by using the tether to fling it to higher orbit from the shuttle, it turns out it was in orbit for about 700 days. So that's a big swing in mission life, and there's no fuel use. It's purely the momentum transfer and the tether fling it to higher orbit. Now, you don't get something for nothing. The shuttle obviously goes down lower, but since we have a very little mass on the SEDSAT and you have a very large mass on the shuttle, the shuttle moves only a little bit compared to the stage there. However, what's kind of nice about it is, let's say if we use that technique for a Delta II, now you've got a tether dangling, and you've sent this Delta II to a lower orbit, so now you've thrown a satellite to a higher orbit. I've now got a spent stage that's going to come back to Earth quite quickly, and again reduce the issue of the problems of orbital debris. Another thing that is of interest is power generation, and that's what you see in this figure right here. It turns out if you ran a copper wire through the Earth's magnetic field, just like any generator, you get current, just like your own little motors and what have you. And that's what they did on TSS-1 and 1R missions, where they actually were able to generate current. Actually, in 1R, they generated enough current that more than their mathematical models had predicted, and there was an imperfection in the jacket, and it arced and fried the tether and cut it, and there it went. So, but even though it cut the tether, it demonstrated that yes, they can generate current far more than they expected. And of course, the last application that we're looking at is atmospheric science, and that's the mission that we're looking at doing in the year 2003, and that's called AirSEDS-S. And that's going to be a probe that's going to be deployed on a 90-kilometer tether. That's almost a tether the length of Lake Michigan here. And it's going to be deployed from the Space Shuttle Orbiter downwards, and we're going to drag it in the Earth's upper atmosphere. Actually, the first day we'll go down to about 160 kilometers, and then we'll deploy the balance of the tether so the probe dips down to about 130 kilometers, and after a couple of days, that tether will be severed and the whole system will fall back to Earth. We're not planning to recover this satellite primarily because, the concern is, let's say that satellite can survive, and let's say the tether prematurely breaks. Well, then that satellite will come down who knows where, and insurance providers and stuff like that don't like random satellites falling down on urban areas. So it's actually designed to burn up. But this is a mission that my company is going to be flying in 2003. We start the Phase B study in the fall for this satellite, though we're having a science workshop this next month reviewing the instrumentation and starting the definition and the final pricing of all the hardware. Before NASA releases the balance of the money, they want to make sure, is this not only feasible, how much is this really going to cost? And then we can lock those costs in. One mission that was of interest that I spoke about a moment ago was SEDSAT. And this is actually a sketch from their manual. And what they're really looking at doing is ejecting, here's the SEDSAT satellite and the SEDS deployer, and ejecting it. And you see it goes through the process where once they get at apogee, they cut the tether from the shuttle and fling the payload to a higher orbit. And then later on, they cut this tether also from the satellite itself. And within about a day, the tether itself falls back to Earth and burns up in the Earth's upper atmosphere. The problem they have with this mission, the reason why it didn't fly, and this actually became to light after the tether cut issue on the TSS 1R mission, is that let's say that deployer system snags 50 feet away from the shuttle. That satellite will want to go out, snag, and then slam back to the shuttle. And the crew does not have enough time to respond to that snag condition. Another problem that they have is not only 50 or 100 feet, but let's say even a kilometer. It actually wants to bounce back about 50 feet, and then you've got a collection of that tether down here. Another concern that they have with this mission is that let's say now we're fully deployed, this tether is under tension. If you cut it, it will want to recoil back to the space shuttle. And you can see, did I bring that here? Okay, here's an example here. Let's say we've got the tether deployed and we get a cut 500 meters from the shuttle. Okay, that tether gets cut by a micrometer. The crew actually will find out, you can see here, in a fraction of a second, okay? But they have only 2.2 seconds to respond and move the shuttle away from that tether before it completely tangles the shuttle. Now, realistically, do you think the crew is going to respond fast enough to turning on the engines, moving out of the way and everything? No, they cannot. And of course, having 500 meters of tether wrapping around the shuttle is not a fun event. It literally ends up, if not handled right, a loss of the shuttle and the crew. And of course, so not only the tether severing is the issue, but really the tether recoil becomes a problem. And that was part of the problem with the SEDSAT mission, is they spent 6-7 years working, I'd say 6 years on several of the safety issues, and they couldn't really get beyond the phase 0, phase 1, because this could not be addressed. And it became even more of a problem after TSS, because with TSS, well, they kind of turn somewhat of a blind eye on things, but when the tether severed so easily, they started rethinking everything. That they wanted to be a lot more cautious in a flight like this. Last year, I believe it was last year at this time, my company was awarded a contract to address these safety issues for NASA, saying, well, we want to fly tethers. We know it's no problem on a Delta because, well, if we get a recoil, who cares? It's a spent second stage and the mission's already over. We're not messing up a primary payload and there's no human life involved. But if we want to escalate this to being a commercial product where we don't tangle with $100, $200 million satellites, or we want to go on the shuttle to International Space Station, this is something that has to be addressed. So my company actually was awarded an SBIR grant, a phase 1 grant, to address this problem. And we did in 6 months, actually. I don't know if it's because we're a smaller company and we can focus on the problem a lot better than having 100 engineers working together at NASA or what have you. But we addressed the problem, and we were awarded phase 2 funding. The original plan was we were going to test out this system, these tether safety systems, on a sounding rocket flight. But NASA felt that right now they're at a critical juncture because they've not had a 100% successful tether mission yet to date. They've had nearly successful tether missions, but if you want a reliable commercial system to sell to customers for momentum transfer and other issues, this needs to be addressed. And so what they did is they took our flight and said, Andrew, we're no longer flying on a sounding rocket, you're going to redesign it for the space shuttle. And we're going to test it there, because if you can flight qualify for the shuttle, then you've pretty much got all your other launch vehicles handled. And so hence came the mission, the ASTOR mission, which stands for Advanced Safety Tether Operations and Reliability. And actually this flight, this name actually came up, originally it was called AirSIDS-ST after the AirSIDS-S mission, which is our atmospheric mission. But it was getting too confusing for them, and the NASA project manager I'm working with picked this name, and since he's letting me fly in the shuttle, he can name it anything he wants, right? So anyways, the whole idea behind this mission is we're going to take a small payload and eject it freely and cleanly from the space shuttle orbiter. And once it's a sufficient distance away, it'll separate into 2 halves and be connected by a 2-kilometer tether. Our goals of this flight are to flight qualify our tether safety systems, to demonstrate also our new deployer system. We're using a completely new deployer system compared to TSS and SEDS missions. We want to also test out an instrument that's going to be flown on AirSIDS-S. We're going to test it on this flight. And lastly, we want to set this up as an education outreach for K through 12, or anyone for that matter. Mission overview, like I said, we're going to eject from the shuttle completely from a gas canister, actually. So this is a small payload. It's going to, once we're sufficiently safe distance away, we're going to separate into 2 halves. And actually, up until it's completely away from the shuttle, they consider this whole unit a bomb, literally, because the issue is let's say if that satellite prematurely separates in the cargo bay, it'll ruin your day, I'll guarantee it. Also, you got satellite and tether tangled everywhere, okay? So before the right, up to the instant we're separated and ejected, this satellite is a dead brick. It cannot function, it cannot do anything, it cannot separate, nothing. It has redundant clamping mechanisms to prevent it from prematurely separating. The minute it's ejected, the power systems go on, the computer systems go on, the sensors go on, and the video cameras go on. Again, once a sufficient distance away, we then separate, and the emergency deployer system and our SOC configuration, which I'll show in a second, then takes over. Our altitude will be 375 kilometers, and we're going to be at an inclination of 51.6 degrees. So we'll be just in orbit, just below the International Space Station. By picking this range here, it actually allows us to fly on a space station mission, so we're not limited to what flights we can go on. And our mission duration right now, for our mission for testing out our tether systems, is 90 days. But we haven't finished the modeling yet. This could be in orbit longer. The big question is the solar flux and the solar wind on the tether. And again, we're looking at year 2000 launch. And the first, the prototype hardware, actually 2 copies of the deployer system, are being fabricated next month, and the satellite will be fabricated in August. And we're going to build, since it's so cheap to build, we'll probably have 2-3 copies of this satellite built over the next 6 months here. This shows you how it's integrated in the canister. The only thing that's different here is we're not going to use this opening door mechanism. The issue is from a safety point of view on the shuttle, if anything breaks loose inside the canister, once that door, you have to guarantee that nothing floats out of the canister once that door is open. So even though so our feeling is if we have to worry about for an open door condition once we eject, let's forget the door then. And the benefit about forgetting the door then is I can make my satellite a little bit longer and have antennas sticking out the top without having to worry about a door. And there's one less mechanism again for them to worry about, because they've had a couple cases where the door either doesn't open or doesn't close, and you have to be able to survive. If the shuttle has to make an emergency landing, you have to be able to make sure they can that you're not going to come loose. So either way, we're going with we're going to remove the door. The other thing that we're going to do is try and simplify this launch, because as you can imagine, with an SBIR grant, it's very expensive to do a shuttle flight, and SBIR grants do not cover shuttle flights. And in the case of the ASTOR mission, NASA is providing a lot of supplemental funding. This is a very good Christmas. Getting an SBIR grant and the shuttle flight that they covered makes for very happy holidays, I gotta tell you. But we're trying to stick with as many standardized systems on this flight as possible and focus on the safety systems itself. And this diagram shows kind of in different stages conceptually what it looks like. And this is actually an earlier diagram, because now the satellite's not cylindrical, it is hexagonal here. Let me show you really quick what we're going to use for. I can't show you the whole deployer system and its design yet because of its uniqueness, and right now we're trying to get the patents all taken care of, and all the secrecy and stuff. But one part I can show you is part of the deployer system has on one of it. Some of you've seen this already. Is we're going to have the tether on the outside packaged as a sock. Okay, and this is one of the benefits of having children. We see cartoons all the time and everything. Well, if we get a snag condition, something knots up in the primary deployer system, what will happen is this encounters a snag, and then the sock freely comes out. So what's nice about it now is I've got something that freely comes out, so this still deploys without a problem. And this tether is nicely packaged here. And this actually represents about 2 kilometers of tether right here. So this is actually our whole ASTOR mission right here. But we're not going to keep it all on a sock. We're going to keep the first 500 meters as a sock and the balance of it on a spool assembly that's going to be in our new deployer system. We talk about, I got a few minutes here and then I open up for questions here. Our education program. What we're looking at doing here is the primary focus of our mission, like I said, is to test out tether safety systems, the deployment, and making sure all the safety systems work as planned. That whole part of the mission takes an hour and a half. And then our mission is done. Now we're stuck, I shouldn't say stuck, now we got a satellite in orbit for about 90 days with plenty of available room for science payload. And that's where the University of Texas at Dallas came in, and they brought in Texas Space Grant money. And what they're going to do is they're providing supplemental funding for not only their instrumentation to go on this free ride, essentially, but also what we want to do is put on some thermocouples and utilize the video cameras that are going to be monitoring live the deployment. We want to take that data and the GPS data and make it available to the public. And so we're going to be transmitting the video and the data information on the amateur radio bands. And that's where we start right now. Hopefully in 2 years it's all taken care of before launch. And the idea will be then is that anyone on the planet, especially with a high inclination like this, will be able to talk to this satellite. You won't be able to send an uplink, but you'll be able to collect information and find out the status and even look at a video image as it's going right over your house. Okay. And for those schools that cannot afford an amateur radio setup to pick up this signal, then what we're looking at doing is we're going to be tracking it ourselves, certainly, and rebroadcasting the data through our project website. And on that website, you'll see not only the orbit track of the mission, where the satellite is currently located, but also what the current data readings are, and then students can customize their experiments around that. That website right now is www.airsids.com. You will not find this stuff yet, only because we're not even in orbit yet. So this is something down the road. But if you want to watch out, this is the place to look for this. And not only for the AirSids-S and the ASTOR mission, but our target is to eventually have one tether mission a year. And we're going to find out in another couple months about a 1999 mission that we're trying to have. So right now we're beginning to see falling place the tether mission 99, 2000, 2003, and our goal is to have 5 a year starting in the year 2001. We're taking an aggressive approach to commercialize tethers in space. We've had a lot of commercial interest now from the big players, and they want to see how this works out. And then ideally what will probably happen is we'll be licensing our technology to like a Lockheed Martin or Boeing and be available for mass use on many launch vehicles. Well, this concludes my presentation. I'm open to questions. Yes.
Is the ASTOR going to be visible from Earth?
Yeah, that's a good question, because the tether on SEDS, being a 20-kilometer tether, was visible to the naked eye as a string in the night sky. As a matter of fact, let me take a step back and then answer your question about ASTOR. On the AirSids-S mission, if you take I'll give you a sample here, a string like this, okay, and hold it to the night sky. Let's say you got a clear night sky out and you got a moon behind you and put this back here. This is exactly how large the tether will look in the night sky on the AirSids-S mission. So it's going to be this very profound structure in space. And yes, we realize the marketing potential of this is extremely enormous, since it will be the largest structure ever flown in space and the most visible thing in a high inclination orbit. Now, with ASTOR being 2 kilometers, my suspicion is you won't be able to discern the string structure, but we're still using spectra, which is highly reflective, so it'll be as a bright dot, about like a magnitude 4 star in the sky. So it should be fairly distinct. This obviously will be very, people get religion fast when they see this orbiting. And ideally, this will then get people thinking about this concept of large structures in orbit around the Earth, that it can be done, and thinking about, again, the possibilities of space tethers.
You mentioned you being able to throw a small satellite up. Could it be that can you transfer energy enough this could become a routine part of deorbiting the shuttle, so that you have small payloads that would then get a significant boost from their deorbit energy?
Actually, not as much from deorbiting the shuttle, because they like to have that nicely controlled and everything. However, there's talk about using space tethers for reboosting the space station, because you can go one way or the other, not only down, but you can go up. NASA's take on it, on using it for the space station, for example, they find it very exciting, very neat, very interesting. They want to do it, but they first need a space station up there, and they need even one segment of the space station to work to reboost it. Though another actually area they're looking at using tethers, that you just reminded me of, is if they're looking at a backup plan, if there's a failure of the reboost system, or with the Russians on their component, is there's enough fuel on the space shuttle left over that they can take a tether, hook it up to the space station, and tow the space station, just like a boat, to higher orbit. And and they want to keep far enough away, about 2 kilometers away, so the plume from the shuttle does not affect the space station. That's proved viable, but right now NASA's focusing on one thing, just getting the space station up. But we are looking at that option for Delta.
What kind of material do you make the tethers out of?
This is actually a Spectra 1000, which is in your fishing line and dental floss. What's that?
It's like a nylon.
That's right, exactly. And it provides sufficient strength for what we're looking for on AirSid's missions here.
Is that the approximate?
This is actually the size that we're flying on most of the 90 kilometers on AirSid's S is this right here. So, yes.
How big is the diameter?
On this mission, the ASTOR mission, it's going to be 1.5 millimeters. On AirSid's S, it's going to be, actually the first 2 kilometers is going to be this really thick stuff right here. I call this my dino dental floss. You know, we had the regular dental, this is dinosaur dental floss right here. I guess Godzilla would know this. You can pass this around actually. The reason why we're going with the thick tether is its likelihood of being cut by a micrometeor for that tether would be in a range of approximately 2 years for a 2-kilometer tether. So from a severing point of view, this is how we're going to address the recoil from the shuttle. There's actually other things, but I can't discuss that. That's international secrets or what have you. But anyways, and then it tapers down to 0.9 millimeters on the bottom 10 kilometers of the tether. So it goes from really thick to very thin. The reason why we go very thin at the end is that there's enough atmospheric drag that if you look at the tether, it doesn't go straight. Near the end, it has kind of a hook to it from the atmospheric drag. Even though you're up in space, you're going fast enough that it's dragging the tether back. How are we doing for time here?
Pretty much done.
What's that?
Pretty much done.
So any more questions? I can answer them after the session's all over. Meantime, I think they need to steal my monitor, right?
Yeah.
Okay. So, all right, thank you very much.
Hi, everyone who's staying for the next presentation about the Space Dock Surfers. The reason Andrew and I decided to combine this was because we're both from West Michigan. We know each other, we work together, and I didn't walk on his toes, and he didn't want to walk on mine, so we just kind of decided to, share the space. And so that's why we did what we did here, in case there's some confusion in all that.
Also, one thing I should add here, he's going to be talking about the business and investment side. And, well, there you would have really owned it then. Is that this company, to give you an idea, started out at annual sales, 4 years ago of $6,000. And next year we're projecting $5 million. And then the year after that, we know we have already earmarked $15 million in sales. So this went out from a basement. We were so poor, couldn't even afford to do this in a garage. So we've gone from the basement to right now, if we get our next mission goes successful, we're projecting $200 million in sales. This is all out of small business. So if you want to start thinking about space commercialization, what have you, I can definitely vouch it can be done.
Yes. Well said.